Okay, so final boss, you pass 251 with A+, and you get through CMU, you graduate, you go for a job interview with like a big corporation. And of course, they ask you tests on the interviews. So let's say you're interviewing with Lawful Evil Corp. They promise you at the interview there's a test. They give you a qubit in some state test. It's either ket 0 or it's ket 0 rotated by 1.8 degrees. It's just like, and the question is yes or no. Is test the 1.8 degrees thing? I call them lawful evil corp because they're lawful in the sense that this promise, you believe this promise, it's valid. Like you believe them, that they've genuinely set it up to be this one or this one. That's evil because this is a very hard test. So, okay, just by the way, it's 1.8 degrees. That's, well, it's like pi over n radians, where n is 100. Okay, so I'm just going to call it pi over n. Think of n as a big number, but you can also, in the back of your mind, imagine it's n. It's 100. So for this, I'm going to do the analysis where we only focus on one-sided error. You can think about two-sided error for this case. But let's focus on one-sided error. So for one-sided error, it's either like a blue vector here, or it's this like tiny vector here, tiny angle vector here. Let's not even worry too much about like which we want false positive, false negatives. We'll just measure in the standard basis, which is okay. That's like has one of the basis vectors on top of one of the possibilities. Okay, so our algorithm will be measure in the standard basis, the 0, 1 basis, and if we get outcome 1, we'll say yes. And in this case, we'll I guess, astonishedly and happily say yes, right? Because actually, the only way you'll get outcome 1 is if the true vector was like the rotation by 1.8 degrees vector. If the true vector was 0, you would never get 1. So you're like, oh my god, it's unbelievable. I got the outcome 1, I can say yes. If you get the outcome 0, which you're probably going to get, well, let's say you say no reluctantly. Not amazing. Okay, well, let's do the easy part of the test. Case 1, or the easy part of the analysis. Let's say test vector really is ket 0. Then the correct answer is no, and you'll never say no. Sorry, you'll never say yes. Yeah. So then, correct is no. So the probability you're correct, or the probability you say no, or that you get the measurement outcome 0 is 100%. Okay, so that's good. But of course, the probability that you are correct in the other case is going to be extremely small. So case 2, when test is this slightly rotated vector, the probability that so the answer is yes. Correctly say yes. Okay, so it's like this is the true vector at angle pi over n, and you're like, what's the chance if I measure in the standard basis, I'll get this one? That's like it's this height squared, or like this height squared, which as we know is basically the same as the tiny angle. So it's sine pi over n squared. Which is sad because this is, pi over n is small, so we know that sine of a small number is basically the same thing as that small number. So it's about pi over n squared, which is about 10 over n squared. And that's really sad. Because in particular, if like n is 100, as it was in my example, this is 10 over 10,000, it's 1 in 1,000. So your probability of being correct is like 1 in 1,000. This is terrible. So probability of correct is about 1 in 1,000, if we're in this 100 example. Now, maybe you're like a little bit used to like college, and you're like, hey, can I retake the test? Like maybe you go and like say like, hey, Lawful Evil Corp, this is a very hard challenge. Can you give me another copy of test? Same copy. Okay, so now we're going to exactly imagine this scenario, and it's a big difference before. So far, like in all this story, like the test giver has only provided you with one copy of the state. And by the way, it doesn't matter if you do destructive measurements or non-destructive measurements. It doesn't matter. Like you can only kind of measure it once to get any useful information out. As soon as you measure it, like you have there's no chance to get more information out of the state. But if like the Lawful Evil Corp will give you like 100 copies of the state, like the same copies, like either 100 copies of 0 or 100 copies of this like slightly rotated version, then maybe you have a chance. So let's say they're a bit nice, and you can get, let's say, num copies of test. Then I think you would do this algorithm. Let's call this algorithm distinguisher. Let's say, okay, for I equals 1 to num copies, then I'd measure the ith qubit that they gave me, the ith copy, in the standard basis. And if the outcome is 1, that's the case where I'm like, holy cow, it's like yes means yes. Like, this is amazing. I'm sure, actually, that test is the slightly rotated thing. It couldn't be ket 0. So then I can, like, say yes. And I can even halt if I want. I mean, I'm like, there's no point in going on. I know for sure it's yes. Otherwise, if I get all through the copies and it didn't happen, then I guess I'll say no. Like every single time I measured it, I got ket 0. I guess I'll say no. Okay. So let's think about how well this algorithm works. And as a warm-up, let me imagine that num copies is 100. Let's say the number of copies is n. Why would I be interested in the number of copies being the same as this denominator? Actually, no particular reason, but let's not introduce too many symbols. So let's try this. Let's ask ourselves, would num copies equaling n be enough? Let's see. Well, this overall distinguishing algorithm also has one-sided error. If this overall distinguishing algorithm ever says yes, and you're sure it's correct, or conversely, if the true answer, let's write it here, case 1, the true answer is actually 0, distinguisher will always output 0. Okay, so this is sort of no false somethings, positives. So the real analysis is like the other case, when the case when test is the rotated vector. So every time it's the rotated vector, and like we keep measuring each copy in the standard basis, and we keep hoping that we see like ket 1, and then if we do see ket 1, we're like, oh, thank God, we can output yes. But like we have to worry about the probability we never see it over the course of the whole algorithm. So yeah, so the probability that distinguisher outputs yes, which is the correct answer, Well, it's really like you're rolling a die that has, okay, it's like you're flipping a coin that has like 10 over n squared chance of coming up heads, and you keep flipping it hoping for heads. Are you going to get it? That's exactly what's going on here. So it's the probability that you see a 1 on the I equals 1 trial, or you see a 1 on the I equals 2 trial, or you see it on the nth trial. Now we have an OR of a probability of an OR in events. So you will always, I hope, know in your life to use the union bound, which says that the probability of an OR of a bunch of events is at most the sum of the probabilities. So this is at most probability that you see a 1 on trial 1 plus the probability you see a 1 on trial 2 plus ... There's like n terms. But unfortunately, each of these terms is at most, as we saw, 10 over n squared. Well, it's like num copies times, but I chose num copies to be n. So that's like 10 over n. And that's kind of sad, because that's still like a small number if n is 100, and even smaller if n is way bigger than 100. So this goes to show that, if the angle is 1/n of the way around the circle, or half of 1/n of the way around the circle, and you get n copies, it's not enough. Actually, your probability of success is still real small. It's proportional to 1 over n. Okay, but on the other hand, I do want to illustrate that, if you get enough copies, you are in good shape. And the enough copies is around n squared copies, which is hopefully believable. It's like you're going to have flipping a coin. The probability if it comes up heads is proportional to 1 over n squared. You're trying to get at least 1 heads. Should be enough to flip it n squared times. So let's consider that. Now let's say we get, say they're really nice to us, and we get num copies to be n squared instead. Well, this part is still the same. There's still no false positives. But now, in case 2, let's ask, is it likely now that distinguisher will say yes? And the answer is yeah. So the answer is yeah. The intuition is, okay, the actual calculation is like a standard thing. If the probability of heads is a p, the probability that you don't get any heads is 1 minus p to the number of copies. In the notes, I wrote that down a little bit more carefully, but let me just, since we don't have too much time, say the intuition. On each measurement, you have 10 over n squared chance to get a 1. But you're doing n squared measurements. So if I asked you, what is the expected number of 1s you get, assuming you don't do this halt, let's just say it's okay to not do this halt. If I just did all the copies, what would the expected number of times I would get see a 1? Well, you have n squared measurements, and each one has a 10 over n squared chance of coming up 1, so it'd be 10. So in this experiment, if you didn't do the halt, this would print yes 10 times on average. Now that's actually just intuition. That's not the same as proving with high probability you'll get at least 1 yes. But that is true. If you look at the notes, you can see the probability this distinguisher is incorrect, in this case too, that it gets all n squared measurements are 0. And so it overall gets down to here and says no. That's at most e to the minus pi squared, which is less than 0.00052. Okay, so you have a 99.95 chance of being correct with this algorithm. So let me summarize in words, and then we'll be done what happened. So for this test, with the angle being like really small, like pi over n, we saw with one copy you're really screwed. The chance that you'll succeed, you have one-sided error always. The chance that you'll succeed is proportional to 1 over n squared. Even with n copies, you're still in big trouble. The probability of you succeeding is proportional to like 1 over n. But with n squared copies, actually you're in good shape, and the probability of you succeeding is like 99.9%. Okay, so it goes to show that even if the angle is small, with enough copies, you can eventually solve these tests. So next time, we're going to do the following things. First, we're going to really confirm that in any of these tests we talked about, if I just give you one copy, you cannot succeed with 100% chance, unless it's your mom or your dad who give you like perpendicular tests. But if the angle is anything other than 90 degrees, one copy is not enough. And this fact, which you might call the no distinguishing principle, is equivalent to what in quantum is called the no cloning principle. So we'll see the no cloning principle next time. And the final thing we'll see next time, which is a really important component of quantum algorithms, and at the heart of Grover's algorithm, is that if Lawful Evil Corp makes their tests by running some quantum code, and you break into their headquarters and steal the source code, even if you can't tell what the rotation angle is, access to the source code lets you beat this test with about n copies. So somehow access to the source code lets you improve this n squared to n. So that's what we'll see next time.